Okay, so I want to go ahead and talk a little bit about redox reactions and how they are useful. Some of you might be aware of these batteries where you plug things into a piece of fruit or a potato, and when you connect them, the light turns on. These things are real. This does really happen. However, as we will see, it is not the fruit itself that is providing the energy. The fruit is part of it. The fruit is an important part of it. It wouldn't work without something like that. But there's another part of this process, which is where the electricity comes from. So what we'll be doing here is we'll be looking at how we can arrange things in a way where we can basically get work out of the fact that a particular reaction involves the transfer of electrons. To start with, there's a couple of definitions we want to discuss. So the word electrochemistry is what we refer to as the study of redox reactions that either produce an electrical current or in some cases might require an electrical current in order to actually take place. When these reactions take place, we have a conversion between different forms of energy. We have chemical energy as one form, and we have electrical energy as the other form. You can go from chemical to electrical, or you can go from electrical to chemical, depending on the situation. When these reactions happen, where we convert chemical energy to electrical energy, we call this an electrochemical cell. There are two possibilities here. We have what's called either a voltaic or galvanic cell. These are situations in which we have a spontaneous redox reaction, and because it's spontaneous, it will create electricity. We can use that electricity to do whatever we use electricity to do. So we can use that electricity. So that's one possibility. Either voltaic or galvanic is the name for that. The other possibility is what's called an electrolytic cell. And in this case, the electricity is used as the force to cause a non-spontaneous reaction to occur. So it's forcing a non-spontaneous reaction by providing electricity as the form of energy. We'll start with voltaic cells, and then eventually we'll also talk a little bit about the electrolytic cells. Here is a schematic of a simple voltaic cell, and I want to go ahead and talk about the parts of this and what's going on here. So in any voltaic cell, you have two very important things. One thing that is losing electrons, one thing that is gaining electrons. So it's a redox reaction. We're gaining and losing electrons. So that's what's the most important here, is that that is happening. So we can look on here, we can see that the electrons are coming from here. They're going in this direction to over here. So this is where we are losing electrons. We can see here the specific reaction that's happening. It's this reaction we're showing here, but here we're kind of showing a picture of what it might look like. So what happens is the zinc loses electrons. As it loses electrons, it becomes an ion, and the ion is then dissolved into the solution. So we have zinc becoming zinc ions and losing 2 electrons. So that is the half reaction that is occurring in this cell of the voltaic cell. The place where this reaction occurs is called the anode. Okay, oxidation occurs at the anode, so we're losing electrons there. Those electrons will go through the wire, and they could do something. They could turn on a light, do whatever other work you want them to do, and then finally come to the other cell. At this cell, we have this reaction occurring. We have copper ions gaining electrons to become a copper metal. Okay, so we're showing the gaining of electrons. A copper ion turns into a copper metal. So those electrons are coming from the other half of the cell, so they're traveling through this wire into this is called the cathode. So the cathode is where the reduction takes place. So we have two types of electrodes. we have an anode where we have oxidation, we have a cathode where we have reduction. Those are the two things that are important to have a voltaic cell. The other thing that is important is that we have them separated from each other so that the electrons have to pass through a wire to go from one to the other, and while passing through that wire, that's where we can get them to do some electrical work. Over time, what will happen, a couple things will happen. The anode, we can see we're turning solid into ions. Over time, this will go away. It will dissolve into solution, and it won't be there anymore. So if we wanted it to continue, we would have to somehow replace that. Over here, we have the opposite. We have ions in solution adding to the electrode. So over time, the ions in solution would go away. So over time, we would not expect this to go on forever unless we were replacing electrodes and solutions. As it's occurring, so we have this negative charge going in one direction, we also need to make sure there's a charge balance that's maintained within each of the cells. In order to do that, we have what's called a salt bridge. Negative charges move in the direction where we lost electrons. So we'll have, here we're showing nitrate ions will move into this beaker as the electrons move out of the beaker through the electrode. At the same time, on the other side, we have copper ions moving out of solution into the electrode. They have a positive charge. So to replace those, we need to have potassium ions move into this part of the solution. So we have the salt bridge as a way to make the system work by allowing us to maintain charges even as we are transferring electrons. So these are the components of a simple voltaic cell. You should be able to label each of these and describe their functions. That's something you need to be able to do. So where is oxidation occurring? Where is reduction occurring? What is the anode? What is the cathode? What is the salt bridge? Which direction are the electrons going in? Where are we dissolving into solution? Where is the solution becoming a solid? So you want to basically be able to do think about all of those kinds of things related to a voltaic cell. So a couple of things we're summarizing here. So again, we have oxidation and reduction occurring in these separated half cells. So we have basically half reactions occurring in half cells. Electrons flow through the wire that connects these. We need to have a conductive solid electrode to aid with the transfer of electrons that come through that external circuit, the wire. The example we're looking at here, they are both electrodes are part of the reaction. It's possible, we'll see later, to have electrodes that are not consumed as part of the reaction. And then we also require the exchange of ions between the two half cells, and we have some kind of an electrolyte there in order to maintain that. So these are the important components of an electrochemical cell. Again, these major components, I'm not going to read through each of these again. We pretty much did that as we were looking at the picture, but if you want to see it summarized in a written form, that is here. You can pause if you need to write these down or take a picture, whatever works best for you. So you want to know all of this information related to a voltaic cell. Okay, so once you have done that, I'm not going to show this video now, but if you want to watch this on your own, you may do so. Once you feel like you know everything about a voltaic cell, there's a video here you can watch where there is a person making a voltaic cell. This is from the television show Breaking Bad, which some of you might be familiar with. It is about a chemistry teacher who makes illicit drugs. So people have been asking me about that show ever since it came on. I don't do that myself, of course, But if you watch this part of the show, there is they're trying to make a battery, and they actually the person, the chemistry teacher that is supposed to be the expert, gets it actually backwards. So I want you to watch that, see if you can figure out what he gets wrong in his explanation, and we can maybe talk about that when we come back together. Okay, so once you understand a voltaic cell, understand where the different parts are, we also want to have a bit of a shorthand explanation, because we don't want to have to draw that whole thing. At least some of us don't want to have to draw that thing every single time. So we have what's called cell notation, is a shorthand description of a voltaic cell. So it's a way of basically showing what's going on without drawing all of those details. And people that are aware of how it works can look at it and know what's going on. Often the way this will work is we'll have an electrode, a vertical line, and then the electrolyte is present next to. And then we have two vertical lines showing basically the salt bridge, and then we have the electrolyte and the electrode that are the other part of the cell. The convention is to put the oxidation half cell on the left and the reduction half cell on the right. So when you read these, you would be starting with the electrode where the oxidation occurs. Remember, that's called the anode. So start with the anode, end with the cathode. A couple of things to be aware of here. So the single up and down line is a phase barrier. So that's when you have different phases. So solid and aqueous. In this case, we might in some cases have a gas. And so we'll look at what happens when that's going on. If you have more than one electrolyte in the same phase, you would use a comma to separate those instead of the vertical line. So the vertical line is showing there are different phases here. So solid, liquid, gas, different things there. Sometimes we will have what's called an inert electrode, and if that's the case, you might have more information in this part. And then again, the double line is showing the salt bridge. So we can look down here. So here we're showing an example of cell notation. We're starting with where oxidation occurs, so the anode. So we've got the electrode. We have a single line breaking that, or showing the phase barrier between the electrode and the electrolyte solution. We're also, of course, showing the S and AQ to show the physical states. Then we have the double line to show the barrier of the salt bridge. And then we have the other location, we have the electrolyte. And then we have the single line, and then we have the other electrode, the cathode, at which the reduction occurs. Okay, so this is cell notation. You want to be able to write things in cell notation and interpret cell notation. Here are some examples of this. So what we're showing here is going between the chemical reaction and the correct cell notation that would go with that. So we're showing, okay, so if this is the cell notation, which of these is going to be the correct combination of reactions? And then here we're going from the combination of reactions to the correct cell notation. And then this one is similar in that to the number 6, in that we are going from cell notation to the correct reactions. The difference, as you'll see when you look at it, has to do with the way the charge is balanced. So I'm not going to go through these in detail. I would recommend trying each of these out, and you can check the answers as you go through if you would like to. So a few more here as well. Again, I won't go through these. You can check the answers. It's something, if we want to go through it, we can have some questions during the class time for that if we need to. Okay, in some cases we will have what's called an inert electrode, as I was kind of alluding to earlier. An inert electrode is something that is there just to help the reaction take place, but it doesn't actually change. It doesn't go away as the reaction takes place. So the reaction will be between different parts of the other phases, not of the electrode itself. So here we're showing an example of that. So in this case, we have the oxidation is over here. This is a typical anode where we have the reaction occurring here. So the iron in this case would be dissolving, electrons flowing away from it to the cathode. But the cathode, at the cathode, there's a different reaction occurring. Here we have the reaction is occurring in the solution itself. So everything going on here is in solution. The cathode doesn't change. The solution changes. If this were the case, what we would do, so this part of the cell notation is similar to what we've seen before. We have the double line, and then we have everything present in that electrolyte solution. Okay, so we have both forms of the manganese, before and after reduction. The hydrogen ions are also present, and then we have the single line and the electrode. Okay, so can be other things going on where the electrode itself is not dissolved. So an additional example here of that, so you can try that one out as well. Okay, finally I want to look at some important vocabulary that we will be bringing into the course as we jump into the next chunk of material, which we will probably be doing in person. So these are some words that we talk about with electricity, and we want to know what they mean because we'll be doing some calculations to solve for various parts of this. So current is the flow of electrical charge. You can think of it as sort of like how much there is, how many electrons there are, would be the current. The voltage is the difference in potential energy between reactants and products. This is sometimes called the potential. So if you think of potential energy that we've been looking at since Chemistry 1A, we looked at a lot in Chapter 18, it's the same idea. It's a potential energy difference. But we measure it in terms of, we use the term voltage when it's about electricity. Okay, so the bigger that difference, the bigger the potential. Think of it like a waterfall. The higher the waterfall, the higher the voltage. And then cell potential is basically looking at the same thing as the difference between the anode and the cathode in a particular voltaic cell. So cell potential, voltage are kind of looking at the same thing. They are a different thing than current. Okay, so current, again, here's a kind of a more formal definition with some numbers and units. So number of electrons that flow through the system in a given period of time. So typically per second. Units here are the ampere. So an ampere is 1 coulomb of charge flowing each second is the definition of that. And then also related to that, the amount of charge on an electron is 1.6 times 10 to the 19th coulombs. And for the measure of amps, so that is how many electrons per second. So here we're saying 6.24 times 10 to the 18th electrons per second is an amp. You don't have to memorize these numbers. You will have to do some conversions that will involve these. So you want to understand how the units relate. So if you see amps and you see coulombs, kind of look for the units you would need for those to cancel out. One other thing here related to this, so the surface area of the electrode will determine how many electrons can flow. So that will determine something about the current. So that's where that happens. There's a combination of current and voltage that would be necessary for a given electrical device to work. So if you don't have enough surface area, you're not going to provide what is necessary. So you won't have enough amps. If you don't have enough of a difference, you won't have it in terms of potential energy. You won't have enough volts. So there's two different things here that will determine how well these kinds of electrical systems will work. Voltage, again, is a difference in potential energy between reactants and products, sometimes called the potential difference. So units here are volts. The volt is a joule of energy per coulomb of charge. Joule of energy per coulomb of charge. So for each, if you think of the waterfall analogy, for each bit of water that goes over, how much energy does it have? So we're basically looking at the difference between potential energies from start to finish. So the voltage, again, is then what drives the electrons through that external circuit from one half cell to the other. Sometimes the voltage is also referred to as the electromotive force, which is often abbreviated EMF. And then cell potential, again, is this particular difference between the anode and cathode. Is called the cell potential. And that is a type of voltage. And this will depend on how easy it is for one thing to be oxidized, how easy it is for the other thing to be reduced. And we'll look at how we can determine that here shortly. So if we have standard conditions, remember standard conditions from chapter 18, we can talk about the standard EMF of the cell, and we abbreviate that in a similar way. So we have E naught for standard conditions of the cell. These standard conditions are the same as what we had for chapter 18 for the most part. So 25 degrees Celsius, 1 atmosphere for any gases, and 1 molar concentration for any solutions. The cell potential is a summation of the cell potentials for all of the half reactions that make up that cell. Okay, so I think we'll go ahead and leave off there. When we meet in person, we'll start looking at how we make these sorts of predictions in terms of which way the electrons are flowing, how we would construct a voltaic cell to have a particular voltage, and we have some tables for looking up some of this information.